My name is Arka Prabhata Reksowardojo. I'm a postdoc researcher at the Institute of Lightweight Structures and Conceptual Design at the University of Stuttgart, Germany. I'll be presenting the paper entitled Active Control and Energy Assessment of a Prototype Adaptive Structure that Adapts to Loading Through Large Shape Changes, which is a part of my doctoral work that I conducted at Applied Computing and Mechanics Laboratory at the École Polytechnique Fédérale de Lausanne in Switzerland. More than 30% of global energy demand and almost half of all mine material consumption are related to construction industry. Rapid growth of population in conjunction with energy depletion and material scarcity, calling for new and radical solutions to reduce material usage and environmental impact. However, best practice in structural design has led to significant oversizing because the structure is designed to withstand worst-case loads with long return periods. Since load-bearing structures are typically subject to loads that are significantly lower than design loads, it means that most structures are over-designed for the majority of their service life. Adaptive structures can control forces and deflection to stay within the required limits so that the effect of external loading is reduced instead of relying on a passive load-bearing resistance. Previous works have investigated active control vibrations caused by extreme loads such as earthquakes and strong winds for buildings equipped with active bracings. Through integrated structural control optimization, civil structures can be designed to adapt to rare high-intensity loads in order to operate closer to required limits, which results in a better material utilization compared to equivalent weight-optimized passive structures. Material savings, however, are only possible at a cost of energy that is required to operate the adaptive system. And to address this challenge, a new design method has been developed which produces minimum whole-life energy solutions. The whole life energy consists of the energy embodied in the material for extraction, fabrication, construction, as well as the operational energy for control. The whole life energy is a new criterion that allows to obtain adaptive structural systems which significantly reduce material mass, which are minimum energy solutions, thus reducing environmental impacts with respect to conventional passive structures. Numerical and experimental studies have demonstrated that adaptive structures designed through this way have a lower environmental impact as the total energy can be reduced by up to 40% for slender configurations with respect to equivalent passive optimized passive structures. In our current study, we are exploring the possibility to counteract the effect of external loading through large shape changes. We developed a new design method which combines shape optimization with nonlinear shape control. The method comprises of two main stages. In stage 1, the objective is minimization of energy embodied in material through optimization of element sizing and geometry, so that the structure is designed to have an optimal shape under each load case. Under a strong loading event, a change of shape takes place to homogenize stresses, and thus material utilization can be maximized. In stage 2, the actuator placement is optimized so that the structure can be controlled into target shapes obtained in stage 1. A geometric nonlinear force method is employed to solve the inverse problem of obtaining appropriate control commands to control the structure into the required target shapes. The sizing and shape optimization process takes as input the external load and gives us the output the cross-section areas to fit all load cases and target shapes for each load case. It is formulated as minimization of the embodied energy, more specifically the sum of the product of the volume of the elements with material energy density. The variables include the cross-section sizing, internal forces, and the change of node positions to obtain the target shapes. Internal forces are included in force equilibrium, and ultimate limit state to ensure that element forces are kept within required limits with regard to admissible stress and buckling. There's also a fail-safe constraint so that the element capacity is not exceeded in case of control system failure and simultaneous occurrence of the load. This method has been applied to design an experimental prototype structure in order to verify numerical finding and investigate feasibility. The prototype structure is a 6.6 meters long, simply supported truss which comprises 6 bays. The structure is very slender with a span-to-depth ratio of 44:1. The mass of the truss, including actuators, is only 125 kilograms. An equivalent passive structure designed to meet a deflection limit of span over 1000 would have a mass of 226 kilograms. This means that through this method it is possible to save up to 45% of the energy embodied in material mass. The structure is built using a mirror modular truss system with a bolt-type nodes. The decking system consists of frames made of 4 aluminum angle profiles. The frame houses acrylic panels that provide a walking surface. Control system is designed to monitor internal forces and node positions. To monitor the element stress, strain sensors arranged in full bridge configurations are installed on each element. An optical tracking system is also employed to monitor the node positions. Element stress and node positions in a combination with the actuator strength stroke length feedback is processed in real time to infer location and magnitude of the external load. The control framework comprises of two processes. First, the shape optimization to obtain target shapes that are optimal to counteract the effect of loading. Second, the shape control to obtain actuator commands that control the structure into the target shapes. The shape optimization is formulated as a minimization of control effort, more specifically the sum of the square of the actuator length changes. Since this process is employed for real-time control, we develop an efficient formulation through a piecewise linear approximation of the nonlinear problem. Here I present the controlled shapes of the prototype. The prototype is designed to withstand a moving load, which is thought of as two persons with total mass of 200 kg walking on the deck. In this case, I'm showing you the shape when the load is applied on the midspan. And here I present the real-time shape adaptation when the structure is subjected to two moving pedestrian loads. Here I'm showing the front view of the structure loaded by torsion-inducing pedestrian load before and after shape control. In this case, we can see an overall increase of the depth of the structure after shape control. The effect of shape adaptation is overall reduction of the stress magnitude with a maximum mean reduction of stress up to 23%. Also, the stress variability under shape control is smaller with a maximum variability reduction of 33%. Up to 10% of whole life energy savings are achieved with respect to weight-optimized passive structure designed to meet deflection limits of span over 1000. Now we would like to take the overall carbon footprint into consideration. If we consider the actual figures for electricity at EPFL campus, we can achieve a significant carbon reduction of 40%. This shows the significant potential of carbon deferral through the proposed method. This way, we can already make a significant savings of embodied carbon share today, and the operational part may reduce over time thanks to advancement in renewable energy generation. With that, I conclude my talk today. Thank you for your attention.